As your C programs involve more structures and functions for operating on those structures to form abstractions, you'll notice a pattern that many of the functions you write make use of pointers to structures. Well, as we've talked about before, with C, we have more concerns with how we manage our memory because we have different lifetimes that we're focused on. We have automatic lifetimes of stack variables. We have heap lifetimes of dynamic memory that we're fully responsible for allocating and freeing as we wish. And these concerns start to introduce potential places for design to break down in unexpected ways. And so what we're going to try and discuss in this video are some design best practices that if you follow, you can avoid a lot of common mistakes and pitfalls in your C programs. And what we'll try and do is be much more intentional about how we think of where we use parameters that involve pointers to structures and what extra additional constrictions or constraints we can place upon them to give us more confidence in the programs that we're designing and try and avoid many common issues. So to motivate this, let's look at a really silly example. And we're going to be coming straight from the previous video, which introduced the compilation of header files and C files into object files. And we were looking at setting up the idea of a point abstraction. So if I were to look at point.h, you'll notice that we defined a structure point and two functions for working with a point. We can set up a point value, which returned a point value, and initialized it. And we can print out a point, right? And notice that the typing of this point print function is we give it a pointer to a point value, and it prints out a string representation of it. Okay, so let's go into main.c really quickly. And in main.c, what we did was we set up a point value and we printed it. Let's try printing this point value twice. Right? And all we're going to do is just try and call that helper function point print that was defined in the point.h header file. Okay. The next thing I'm going to do, and for the purposes of this video, we're actually going to compile all of our C files together at the same time. We're not going to make use of incremental compilation here. Soon, in a future video, we'll look at how we can use a makefile to manage the complexity of building all of our object files and then linking them together. And that will give us the optimization of not having to recompile certain parts of our program. But for today and for this video, now that you know how object files are compiled, we can do all of that in one step with a command such as gcc wall wextra standard C11. Sure, we'll use compile or debug flags, and what we're going to do is give our C files here. So main.c and point.c. And now we have our file a.out. You might be wondering, well, why would I go to the trouble of compiling those object files? And again, as I mentioned before, as your projects grow, if all we were changing was one file, and here all we changed was main.c, notice we didn't change anything about point.c, then you can get some benefits out of compiling to object files and then just linking them as opposed to recompiling everything from scratch. And that's especially true if you're building really large projects like operating systems or web browsers or flagship games. Okay. So when we run a.out, notice that we get the same point values printed one after the other. Big deal, right? All right, well, let's have some, let's do something a little mischievous here and open up point.c, right? And in this point print function, let's do something a little bit sneaky here. Let's say self x is going to increase by 1.0. Right? Now this is a pretty malicious and intentionally sneaky little thing we're doing here, right? We're increasing the x member of this self struct pointer by 1. And it's a little surprising, right? So I'm saving that and let's go and recompile. I'm just going to run that same command again and then /a.out. And notice that we called point print twice. And this time around, because we changed that pointer that we gave, we changed the member of the struct that was pointed to by the pointer we gave to this print function. It actually mutated that structure that we gave it access to. Now, of course, we just made that change. So this isn't really a surprise. This isn't, like it's very obvious why this is happening. But what I want to dwell upon for just a moment is if we open up main.c, if you are someone who's just reading this file here, and you're just reading the point.h header file, which I previously said that's all you should have to read in order to understand how to make use of these point functions, then this would be a totally surprising result. And it seems kind of strange and a little bit scary, right? That we have a variable that's local. This is a local variable, and we're giving a pointer to it saying, hey, here you can have access to it. And that pointer has both read and write access. So because there's no guarantee that this print function wouldn't write or change this pointer in any way, it had access to those members and could change them. And that feels kind of bad. So what could we do to help avoid this issue? Well, one of the things we can do is make use of the keyword const. So when we're defining functions that take pointers, if we don't intend to mutate what the pointer points to, the value or the object that the pointer is referencing, then you should, by best practice, declare that parameter as a const parameter. Now, I should tell you that this isn't a silver bullet. If someone really, really wanted to, they wouldn't have to they wouldn't have to try very hard in order to have to get around this little bit of a constraint. But what this is this is giving us a signal that says, hey, you give me a pointer to a point, and what I'm telling you by contract and by advertising is I'm not going to change that, right? And so you're thinking, okay, well, you changed it there. Well, what about in point.c? And this is true when you, let me just scroll down. I've got this, I'm gonna make that error a little bit smaller. So you'll notice that we open up this file and we've got an error elevated that says point.c, there's a conflicting type for point print. And that's because we changed in the header file the declaration of point print, but we didn't update the definition here. And what we said was this was going to be a const, right? And notice that I save this file and that error goes away, but now we've got a new error, right? It says we cannot assign to variable self with the const qualified type, right? So by declaring this parameter as const, if we, in an obvious way, try and modify something about that parameter, then we'll get an error, right? So if I delete this line, that goes away. And notice that what we've done, if I go and recompile this, is and we can test it just to convince ourselves that we fixed that little bug that we had introduced. Notice that what we've done is we've given we've made a stronger statement and a stronger advertising. We're telling you here, if you're reading the documentation of this function, I will not change this parameter. You give me this point, you give me a pointer to a point, and this print function isn't going to change anything about it. Now, as I mentioned, in C, there are 1,000 ways to die in the West and in C, and there are ways that you could cast this pointer to something that wasn't const and do some ugly things if you really wanted to be nefarious. But what we're trying to address here is more of an API design concern, and one that helps us avoid making unintentional or accidental errors. And these errors can occur on both sides of our barrier of abstraction, right? So it could be an error of assumption from the function caller. If they didn't see the keyword const, they shouldn't assume that this pointer variable might not change, right? And that it won't change. That's not a very good assumption to make when you don't see a const advertised. As the function implementer, if you give yourself that const declaration, you can help avoid if you accidentally change that parameter without really thinking about the implications of it or what it would mean. Hopefully the compiler gives you an extra warning that it wouldn't without that flag being there, right? So when we start designing these functions that have parameters that are pointers to other values, we should make use of the const keyword as one of the best practices and principles among many others that we'll talk through in this particular video. So as a best practice, the first one that we'll discuss is what we just saw. Notice that when we declare something as const, if we try and change something, the value that's pointed to, then the compiler will give us an error if we don't do anything clever or nefarious to try and get around the compiler's error here, right? And so this signals to the people using the function that, hey, we're not going to change some member of this that's pointed to by this pointer. As a rule of thumb, you should always start with the strongest guarantees possible. And if you don't have any reason for mutating, something that's being pointed to, you should just go ahead and declare your parameters as const. And then, and in fact, as a best practice and as a rule of thumb, you should just declare every parameter as const when you're dealing with pointers. And then when you realize that, oh, I actually do want to mutate a particular pointer, that's when you need to be very careful and think very deeply about whether the design of the function that you're carrying out and the way that you're going about this mutation makes sense. And we'll look at a few cases in just a moment where we have some flexibility when it comes to mutating a value versus producing new values that we might want to consider. Towards that end, there are 4 functions on this slide, and I want you to pause the video here in just a moment. I'll leave the screen and give you a moment to ponder. What are the implications of these 4 function signatures, and what might you be able to derive from how you could assume they work? And assume that we're trying to implement a function named add for points, and we're giving 2 points, and there's potentially a third parameter there in the last option. But if you can just use the knowledge that we've talked about so far and the implications of using the keyword const as a modifier to the type of these parameters, think through how you would expect each of these functions to work, what guarantees they might give you, and try and jot these things down before we continue on. All right, so let's talk through each of these. The first option here is option A, and its 2 parameters are a const pointer to a point and a const pointer to another point, right? So our points are A and B, and if we are to believe this declaration, we should be able to give it 2 pointers, and it's not going to change anything about either of the structures that are pointed to by these 2 parameters, right? So what that means is, well, how are we going to get some result back out of it? How is this going to have any impact on the program, right? Well, the return value is going to be a new point object. And just by intuition, if we were to believe this is a well-implemented and well-intentioned function, then it should just give us a new point value that would be an automatic value we could use however we'd like. That was the addition of points A and B. And this is a new point object that we can use, or value, I should say. And it wouldn't have changed anything about A or B. Now let's contrast that with the next option. So notice the next option, we give it a constant pointer to a point and a non-constant pointer to a point. When you see this distinction, your radar should go up, and you should be very careful, because what this probably means is you can't trust, and in fact, you should probably assume that this B parameter, whatever it points to, that value is going to be mutated in some way by the nature of this function being executed. Now, you'll notice this is a return type of void, so we're not expecting any new value back. And if you were to place a bet on how this function works based on this declaration, it would probably make sense that A's 2 values, X and Y, are being added to B's, and B is actually, whatever B points to is being mutated in some way through addition, right? The inverse is true on the next function declaration. So notice on this line, what we're seeing is the first parameter is not const, the second parameter is const. So here you could assume that the second argument you give would be a pointer to some point struct, and that wouldn't change, it would be immutable. But the first argument would be a pointer to a struct that you would assume is being mutated as a part of this operation. Once again, the void return type is a hint that that's probably the case as well. And the last one is a particularly strange function declaration coming from the world of Java or Python, but is actually quite common when you're working in C. And so we'll notice once again, we're giving two const values, right? And so we're saying these pointers, where you're not going to change anything about the structs that they point to, they are constants. But this last parameter named out is another pointer. So you're having to give another memory address to somewhere that can store a struct point. And what this function declaration is implying to you is that it's actually going to use that memory address to write the results of this operation, to add A and B and store the resulting point addition into this third parameter named out. Oftentimes you'll hear this called an out parameter because it's a means for returning, in a way, a result. And oftentimes these functions that use a pointer parameter in this way, that the intention of it is to return a result back to you, will also have a return value that's very frequently an integer. And that integer often represents whether or not this operation succeeded or failed, or as a pointer that has certain semantics. The fgets function, or fgets, is one that makes use of the very similar construct, right? You give it a pointer to a buffer as one of the parameters, and it's trying to fill that buffer. It's not actually returning to you an array of characters. It's taking some pointer that you give it and filling that buffer through mutation, right? So notice that there are here, for the simple idea of adding 2 points together, we've got 4 options. And we could have done this without pointers, and we could have done this with point parameters that are value types that would have actually copied each of the members into each of our parameters. And that would have been another way of writing some additional functions. But as we start to make use of structures, what you'll find and see is it's much more conventional to just pass pointers to our structures than to copy structures, because the structures can be much larger in size and much more expensive to copy into our functions frame than passing around our pointers, right? But hopefully you can appreciate that we've got a much larger design space of options for designing our interfaces and our functions in C than we necessarily had to sort of worry about in other languages that were memory managed. And this idea that we can give a pointer and to a memory address as an out parameter, this one winds up being quite useful in many different cases. And this is something that you wouldn't have ever done without it being a very strange case in an object-oriented setting. All right, so let's continue on. As I mentioned, we don't have to give pointers, but the reason we do, and the reason why we tend not to just have structs directly as parameters, as this slide is talking about, is because structs are passed by value. Complete copies will be made. And so this is a more expensive operation than copying around a pointer. This is why in a memory managed language like Java, Python, everything is passed by, everything with objects and arrays and lists and your data structures are passed by reference, because it's really passed by pointer, right? And so in those languages, you're passing a pointer around. And the reasons why you needed to be careful reasoning through pass by reference, which was actually, you're actually passing a reference or passing a pointer, is that when you can mutate what that pointer is referring to, you enter the ability to have for functions to create side effects that are surprising and can lead to unexpected bugs in your programs. So you really want to be careful and intentional about your use of pointers. And again, as a first rule of thumb, declaring your pointer parameters as const is a great starting place for consideration. When you are designing functions, one of the common patterns that you'll see in C is if you are intending to mutate a parameter, as I mentioned, you won't see the const keyword in front of it. And if you're trying to sort of mimic an object-oriented design style, you can imagine something like this translate or add function, where this would be a translate function where we've got point self. Let me see if I can make this slightly larger. Oops. Point self, and the next two parameters are x and y, and you're increasing x and y by those two parameters. And notice that because this returns void and you're giving a mutable pointer to self, it's not being advertised as const, you expect that whatever object is referred to or whatever structure is being referred to is being mutated, right? And I should mention that in the slide, and I actually am going to fix the slide really quickly. Self is not a keyword in C, but we're going to choose self in this course rather than this, because when we get to using unit tests, we'll see that for reasons beyond our concerns right now, avoiding the use of the keyword this, which does have meaning in C++, will be helpful to us then. But self is saying, you can think of this very much like a method in an object-oriented language where you had that implicit this keyword. Well, in C, you're just going to have to give an explicit pointer to whatever object or whatever struct you're calling this method on, right? And the second common pattern, which you'll notice, is to have an immutable reference to some pointer and produce or give the reference, give a memory address of some object that you're trying to write to, and allow that to be what we call the out parameter, as discussed on an earlier slide. So let's go try and actually implement two examples of this really quickly. And if we open up point.h from our previous video, and let's set up a function named offset, and offset a point by another point, right? And this will be a void function, and point offset will have a point self that is non-const as the first parameter, and a const point pointer that is the offset by parameter. And just in looking at this declaration, we get the sense that, okay, we call this function, we give it a pointer to some structure that we intend to be the one that's being offset or moved by whatever the next point parameter is. And we assume that second parameter is not going to be changed, right? Because it's, or will be treated as immutable. All right, so I'm once again going to just copy this line and then open up a split screen. So Control W and then V, and then Control W and L for move to the left, or right, I should say. And I'm going to edit point.c. All right, so I'm going to paste in that line to declare, and I'm going to go ahead and, for the purposes of this, quit out of my left screen. Oops, right, and quit out of my left screen so that you can actually see what's going on in the point.c. So what are we going to do? We're going to say self plus equal offset self dereference the x member is going to increase by offset by x, right? And same idea with y, right? In the Python programming language, they actually carry forward this similar convention that you'll see in C programs. And that makes sense because the inventor of Python had a background in C. Python's implemented in C and carries on some of its same conventions, where when you define methods of classes in Python, you have to declare a self parameter. And we'll see that that's actually common when we're starting to think of our C modules in terms of how we might design in an object-oriented paradigm as being similar, where we are giving the first parameter is self, and we'll just have to give it that value directly, right? So I'm going to write that and then open up main.c. And let's go ahead and set up a point B. That's a point value, and maybe 10 and 10. And we can offset, and we can give the memory address of A and the memory address of B, right? Oops. Oh no. Okay. So we are offsetting, and notice from the caller's end here, you have to go on trust, right? We're not saying that we can't really tell the difference between A and B, or these two arguments, as to whether or not one is expected to be mutated or not. There are some programming languages that have come along, like Rust most specifically, and you have to be more intentional on the caller's end to make it obvious from the caller's side of things which of these two might be mutable or not. But in C, we just have to trust that the person who, we as the developer, read the documentation and know that B is not being mutated, A is, all right? So we expect when this program is compiled and runs to be 11 and 12 as the point value printed out the second time around. So if I go back up and recompile, and there you go. So notice we've mutated that first, the value pointed to by the first parameter, the self parameter, and we've treated it sort of like a method call. All right, let's see what else we've got here. We will see other instances of this out parameter style. And what this gives you is a more immutable design, where we're not trying to mutate some parameter that already has values that are important, but one where we're actually producing new values. And in general, where possible, using an immutable style where you're producing new values instead of mutating old values is encouraged, but this comes with some overhead and some other concerns. So the next thing I want to mention is the idea of ownership. And in that slide, I'm actually going to come back to in the next video where we talk about recursive data structures and forming a path or a linked list of points out of point structures and recursive nodes. But I want to motivate this problem by going to main.c and talking really quickly about some of the flexibility that we have in C that we don't have in other languages, and some of the new concerns that ownership will give to us. So the idea of ownership is this question of who's responsible for freeing some value. And in the cases of dynamic memory, we're the ones that are responsible for that. And more specifically, there are going to be variables or pointers that are our programs owning pointers. And we need to be careful that those are the ones that we free so that we don't accidentally double free and we don't use a pointer beyond that value's lifetime. All right, so let's go ahead and include from standard lib the library file so that we can allocate some dynamic memory. And what we'll do is let's go ahead and change A to not be an automatic variable here, right? So notice that A is an automatic variable. Its two members would be stored in main stack frame. Let's actually set up A to be a pointer, and it's going to be the result of calling malloc for the size of a single point object, right? And A is going to be initialized to this point value, right, of 1 and 2. And then whenever we use A, because A is declared as a pointer rather than a point struct, a pointer to a point rather than a point, we don't have to take the address of A. A's value itself, if we were to evaluate it, is going to be a memory address that refers to a struct. So we can just use A directly anywhere we were previously taking the address of our stack variable named A, right? So now our stack variable named A is a pointer. Its value is a memory address that refers to somewhere on the heap, right? Now, and that means that when we go to print, we can give A directly because A is a pointer to a point, right? Whereas before we had just a point, and if we wanted its address, we needed to make use of the address of operator, right? That distinction hopefully will become more comfortable as you are working with pointers and memory pointers and the addresses of stack values. You'll occasionally need to take the address of heap values as well. That's more common when you're working with arrays on the heap and you want to be able to access members directly or items of your array directly from the heap. Okay, so one of the other best practices that I said you should never ever use malloc without testing for null return value. So let's go ahead and take care of that. If A is null, and actually let's go ahead and set up a helper function here. I would encourage you to make use of this helper function in future programs. So we can define a function such as a function that returns a void pointer, call it guard, so out of memory guard. And it's a function that is going to take a void pointer as an input, and I'll just call it P. And I'm going to define this function down below. And all it's going to do is test if P is null, then fprintf to, and I'm going to need to include standard IO. All right. So I include standard IO. We're printing to standard error, out of memory, and a new line. And exiting with exit failure. Right? Otherwise, what we'll do is return P. Right? And now what we can do is use this helper function guard to say guard malloc. Right? So I would encourage you to place this particular abstraction in a header file so that you define guard in some header file, maybe guards.h, and the implementation in guards.c. We'll see this is going to be a function that you probably use in many other places moving forward, so that you don't have to do this check redundantly each time. But there, just to really quickly describe what's going on before we get into back to the main point of this lesson, is remember pointers, no matter what value they point to, they always take up the same amount of size in memory, the size of a word in a system which is 64 bits in a modern machine. And so the type of a pointer really only impacts pointer arithmetic and the semantics around making use of it. And so we can implicitly cast, malloc returns a void pointer, right? So we had a void pointer, we can give that void pointer to guard. It's testing whether or not that pointer address is 0, which is the case that we're concerned with if we're out of memory. And if it's not 0, it returns that pointer address, and then that address gets assigned to a pointer to a point named A. And that cast is implicit here. We don't have to explicitly make this cast. It's totally fine for this to be implicit. Okay, but either way, it was just an address, and it's just how we think about the typing of that, what's stored at the address that's pointed to in terms of its implication. So we have a pointer to a point, and great. So we've made that test. And there's one other thing that we said that we always need to do. If we're mallocing, there always needs to be a corresponding free when you're done with it. So when we're done with it, we can say free A, right? And we should have a well-formed program here where we're taking care of our memory concerns. We're allocating memory for a point structure, and we're freeing it later. All right. So I'm going to, once again, recompile and /a.out. And if I wanted to test with valgrind leak check full /a.out, we would see that all heap blocks are freed. Everything's good. All right. So let's just reflect on this a little bit. We've added some more boilerplate here, and I'm actually going to separate some of this boilerplate so that it's a little bit more obvious. To work with dynamic memory, so memory that we were able to control the lifetime of on the heap, we allocated it, assigned a pointer to it, and notice that one of the values, one of the benefits that we get out of having a function that initializes a structure and returns it as a value is we can use it not only in the case like we did down here on line 14. So notice on line 14, we're saying for this automatic variable named B, which is a stack variable, initialize it to be the return value of point value, and here are these two arguments. We can actually assign to a pointer that's on the heap in a fully initialized structure that was produced by calling this point value function. That's a big win. That's it's really handy to be able to do this. We could not say A is assigned 1.0, 2.0, right? This initialization is only possible when you're allocating a static or an automatic variable. You can't initialize a heap structure in this way. So as a means and a best practice for designing data structures where you're going to work with them, and you might work with automatic variables, you might work with dynamic variables or dynamic memory. It's helpful to have a function that can fully initialize one of these structures for you and get you good to go, right? One of the reasons why we do this outside of our module, right? So notice we're malloking outside of our module, is because now the caller, us from the main function having included point.h as the caller, we get to decide what area of memory is this structure going to be in, right? And then the API of this module is such that because the functions are, hey, you just give me a pointer to the memory that you want me to use, then we can use heap memory where we want, as well as stack memory where we want, or static memory where we want, without needing to make that trade-off at the API level. By virtue of saying, hey, just give me a pointer, we can give that an address to any of those three locations. Whereas if we said, no, give me a value, then the only way we could get a value in, as opposed to the pointer, is to copy all of those members in. Right? So this is one of the reasons why you'll see our module functions tend to be defined with pointers to our values. And so we can mix and match. So notice this point offset function, we gave it the address of some heap memory for the first parameter, and that's actually what we went and mutated. And then we gave it the address of local stack memory for the second parameter, right? And we're able to mix and match these things. So another design principle that you'll see is by making the allocation and the ownership of a pointer or memory the caller's concern, or the person using your API's concern, you are able to make it more flexible the ways that someone is able to use it. And there's going to be one giant caveat there, which is if point value were to have allocated some heap memory on its own, then this API would tell us, hey, before you free point value, you're also going to need to drop, you're going to need to call another function so that our module can take care of that cleanup. And then you can free the memory that was allocated for point value. We'll get into that in the next video, right? So ownership is the idea of who is responsible for freeing, right? And the next video will cover this in more depth, but in your memory managed environments, you haven't needed to think about this concept quite as deeply. With C, you're going to have to think about this and wrangle with it much more concretely, right? So the owner is going to be the variable that's responsible for freeing it, right? And so in our example here, A is the owning pointer to this memory address that was mallocked. And it would have created bugs if when we made a reference to A, right? When we gave A as a copy, the memory address to point print or point offset or point print down here, if any of those functions had freed this memory without us telling it to, then we would have a violation. We would probably have a double free. And so as a rule of thumb, we tend to want to organize our code such that there's only ever one pointer that is considered the owning pointer. And so here, A would be the owning pointer of the memory that was mallocked, and that's why we're freeing A. There are nuances to this, such as, well, what if you wanted to write a function that allocated some memory and then returned that pointer on behalf of someone asking it to go ahead and set this up, and then whatever that return value was, however it was assigned or used, that would be considered the owning pointer. But the point is you really want there to be only one value in your program, or one pointer in your program, that is considered the owner of some allocated heap memory, such that when you need to free it, you know that that's the only one that you need to free, and you're not going to accidentally double free, right? So you should be able to allocate or discern any pointers, any allocated memory's owner, right? And we'll look at recursive ownership and allocations in the next lesson, where we talk about recursive structures with and we'll create a simple linked list, right? We'll see that there are variables that aren't owners, they're just references. And when we think about what happened in point.c, we would think of all of these pointers as not being the owners of any allocated memory, right? We're just giving references and giving access to some memory by that's pointed to by these parameters. But none of these are becoming responsible for owning those pointers, and thus aren't going to have to worry about freeing them, right? And so as a general rule of thumb, ownership is the concern of the caller, and memory management is the concern of the caller. And so this gives us the ability to, from our API's point of view, work with whatever memory they want us to, and avoid accidentally creating interdependencies on who's managing what data. So this was a quick pass on design principles when you're working with C functions that involve pointer parameters, specifically when you're working with structures and thinking about how that impacts dynamic memory versus local automatic memory. Following these principles will help you avoid many common pitfalls and help ensure that your code isn't structured in such a way that you'll be vulnerable to many bugs that can occur when you kind of go about this in an ad hoc way. Gaining more practice with this will be the focus of our next lab going out soon, where we create data structures and some abstractions that involve these types of design decisions.